Welcome to this Introduction to Probability tutorial. In business and life in general, we oftentimes base our decisions on an evaluation of uncertainties. For example, should we take an umbrella would be based on the chance of rain. If we raise our prices, what is the likelihood it will decrease our sales? If we buy a stock, what is the chance that its value will increase? Probability is a numerical measure of the likelihood that an event will occur. Probability values are always assigned on a scale of 0 to 1. A probability of 0 means that there is absolutely no chance the event will occur, and a probability of 1 means that there is a 100% chance of something occurring. A probability of 0.5, which is halfway between 0 and 1, means the likelihood of something happening is 50-50, meaning there is an equal chance of it happening or not happening. So we can say that the occurrence of an event is just as likely to occur as it is unlikely. As we move from 0 to 1, the likelihood of an event occurring increases. So if the weatherman says there is a 0 or near 0 probability of rain, then that means there's almost no chance or no chance of rain. But if the probability of rain is 0.9, then it is more likely to rain than not. In fact, it will probably rain. If the chance of rain is 0.5, then it means it is just as likely to rain as it is not to rain. As part of our discussion on probability, we have to define an experiment. An experiment is a process that generates well-defined outcomes. So for example, we might define an experiment as tossing a coin, rolling a die, inspecting a product we sell, or conducting a sales call. Each of these experiments would produce an outcome. For example, tossing a coin would produce 2 possible outcomes, a head or a tail. Rolling a die would produce 6 possible outcomes, a 1, 2, 3, 4, 5, or 6. Inspecting a product might have 2 possible outcomes, it is defective or not defective. And conducting a sales call would have also 2 possible outcomes, sale or no sale. By specifying all the possible outcomes, we identify the sample space for an experiment. The sample space for an experiment is the set of all experimental outcomes. A sample point is an element of the sample space. So for example, if we consider an experiment where we toss a coin, the coin can either land on heads or tails. So we let S denote the sample space, and we use the following notation to describe it. Heads and tails, the 2 possible outcomes, are listed within the brackets. We can do the same for the sample space for rolling a die or for conducting a sales call. In order to calculate the probabilities associated with experimental outcomes, we need to learn some counting rules. The first counting rule applies to multiple-step experiments. Let's say we toss 2 coins. In this multi-step experiment, the first step would be the toss of the first coin. The second step is the toss of the second coin. So we toss 2 coins, and each one of the coins has 2 possible outcomes, either a head or a tail. Let's use the letter H to refer to a head and the letter T to refer to a tail. If we think about this scenario, tossing 2 coins, we can see there are 4 possible outcomes. We can either toss a head on the first coin and another head on the second coin, that is 1 possible outcome, or we could toss a head and then a tail, that would be the second possible outcome, or we can toss a tail and then a head, that would be the third possible outcome, and finally we could toss a tail and then another tail, TT, and that would be the 4th possible outcome. So the sample space for this multi-step experiment has 4 possible experimental outcomes. Since we are just dealing with 2 coins and each coin has only 2 possible outcomes, head or tail, it was very easy to list all of the possible outcomes. But we need something called a counting rule for multi-step experiments when the example is more complicated and has too many outcomes to list. Here is the counting rule for multiple step experiments. If an experiment can be described as a sequence of k steps with n subscript 1 possible outcomes on the first step and n subscript 2 possible outcomes on the second step and so on, then the total number of experimental outcomes is given by n subscript 1 times n subscript 2 all the way out to n subscript k, k being the number of steps. So let's translate that first to our simple coin example. We are tossing 2 coins, so it was a 2-step process, so k is equal to 2. And since there are two possible outcomes for the first step, head or tail, then n subscript 1 is equal to 2. And there are two possible outcomes for the second coin toss, so n subscript 2 is equal to 2. So the total number of experimental outcomes is given by n subscript 1 times n subscript 2, or 2 times 2, which is 4. So there are 4 possible experimental outcomes. We saw this easily on the previous slide by listing all the outcomes intuitively, but we need this counting rule for more complicated examples. Let's do a more complicated example. Let's say we want to determine how many experimental outcomes there are if we roll a die 3 times. So in this 3-step process, we have k equal to 3 rolls of the die. Each time we roll the die, there are 6 possible outcomes, with the first die having 6 possible outcomes, the second die and the third die all have 6 possible outcomes of 1, 2, 3, 4, 5, and 6. So the total number of experimental outcomes would be 6 times 6 times 6, which is 216 possible outcomes. So you can see listing all of these outcomes would be very difficult, and using a counting rule such as this makes it very easy to determine the number of possible outcomes. We can draw a tree diagram to help us visualize a multi-step experiment. Here is a tree diagram for tossing 2 coins. You can see all the possible outcomes for this experiment more clearly with this type of a graph. The tree starts on the left-hand side with the first step of a multi-step experiment. In the case of tossing 2 coins, we have 2 steps. Step 1, the first coin toss, results in either a head or a tail. Now we toss the coin a second time, and so for step 2, we also have 2 choices, heads or tails. So if the first coin toss was a head, then from the head branch we have 2 possible outcomes for the second step, either a head or a tail. And if the first coin toss was a tail, then following the tail branch, we can again have 2 possible outcomes, heads or tails. So in total, we have 4 possible outcomes for the 2 coin tosses. If the first coin toss is a head, then 2 outcomes would be either head, head, so we write HH, or head, tail, so we write HT. On the other hand, if the first coin toss is a tail, then we follow the tail branch and have 2 possible outcomes for the second toss, either heads or tails. So now we have 2 more possible outcomes, tail head or tail tail. So there you have all the possible outcomes drawn on a tree diagram, which helps us to visualize the process more clearly. Another useful counting rule is called combinations. This counting rule allows us to count the number of possible outcomes from an experiment when the experiment involves selecting little n number of objects from big N number of objects. Here is the way the formula is written. On the left-hand side, we have a big C for combination with a big N and a little n as superscripts and subscripts. This is written as, in parentheses, big N on top of little n. And then the formula begins. Big N factorial for the numerator, and that's divided by little n factorial times big N minus little n factorial in parentheses. Do you remember what a factorial is? The exclamation point is read as the word factorial, so we say n factorial. This is defined as n times n minus 1 times n minus 2 times n minus 3, and so on until we get to 1. So for example, if we have the number 5 factorial, we multiply 5 times 5 minus 1, or 4, times 5 minus 2, or 3, times 5 minus 3, or 2, until we get to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. By definition, 0 factorial is 1. So let's look at an example. Let's say we have a hat, and inside the hat we have 5 pieces of paper labeled A, B, C, D, and E. How many different ways can we select 2 pieces of paper from the 5 that are in the hat? To use the formula, we have to first get big N and little n. So big N is 5, the total number of items in the population, and we have 5 pieces of paper. And little n, the sample size we are taking, is 2, because we are taking 2 pieces of paper from the hat. So using the combination formula, we get The combination of taking 2 out of 5 is 5 factorial over 2 factorial times 5 minus 2 factorial. So the numerator is 5 times 4 times 3 times 2 times 1, and the denominator is 2 times 1, which is 2 factorial, and then 5 minus 2 is 3 factorial, so it's 3 times 2 times 1. And that is equal to 120 divided by 12, and that is equal to 10. So we have 10 possible combinations of taking 2 pieces of paper out of a total of 5 pieces of paper. If you think about it, you can probably figure out those 10 combinations. They would be A with B, A with C, A with D, A with E, then B with C, B with D, B with E, and then C with D, and C with E, and finally D with E. But rather than think about all the possible ways we can take 2 pieces of paper out of a hat containing 5 pieces, we can simply use the combination formula. Now let's suppose the order we take the pieces of paper out of the hat is important. So it's not just about whether we take out A and B, it's which we took out first. So an outcome of first A and then B is not the same as an outcome of B and then A. The counting rule for this scenario, where the order is important, is called a permutation. And the formula looks like this. We use the letter P instead of C to denote permutation. The numerator is big N factorial divided by big N minus little n in parentheses factorial. So for our example with 5 pieces of paper, if we want to know how many possible outcomes there are of taking 2 pieces of paper out of the 5, but we care about the order in which these papers are selected, do you think there are more possibilities or less possibilities if we don't care about the order? Think about it. Remember what I said. With the combination formula, you don't care about the order, so you take 2 out of 5 pieces of paper from the hat. With permutations, the first piece of paper and the second piece of paper is different than the second piece of paper and the first piece of paper. Even if they're the same pieces of paper, we count them differently. So what would you expect with the permutation formula? Well, we put 5 factorial in the numerator because that's big N, right? And divided by big N minus little n, so 5 minus 2 is 3. So that is 5 factorial over 3 factorial. And we get 5 times 4 times 3 times 2 times 1, which is 120 over 3 times 2 times 1 over 6. And 120 divided by 6 is 20. So we have 20 possible outcomes when we care about the order. Since A then B is not the same as B then A, then the possibilities increase. There are 2 possibilities for every 1 possibility in the other example. Now that we understand how to determine how many outcomes are possible, we have to learn how to assign probabilities to each of these outcomes. In statistics, we have 3 different approaches to assigning probabilities. The first approach is called the classical method. It is also known as a priori classical probability. The probability is based on prior knowledge. So for example, we all know that a coin has 2 sides, heads and tails. So assuming it's a fair coin, we can assign probabilities because we have prior knowledge about the process. And we would say there's a 50% chance of a head and a 50% chance of a tail. We can do this with a deck of cards as well. What is the probability of picking an ace from a deck of 52 cards? Well, we have prior knowledge that there are 4 aces in a deck, so the probability is 4 out of 52. If you use a calculator, you'll get something like 7.69% chance of picking an ace out of a deck of cards. A second approach to probability is called the relative frequency method, or the empirical method, because it uses observed data or empirical data to determine probabilities, not a prior knowledge of the process. So let's say I observed from the past that 5% of parts inspected at a factory are defective. Then the probability of randomly selecting a part being defective is 5%. This is a probability that is assigned based on past observations. And then the third method of assigning probabilities is called the subjective method, where based on past experience, personal opinion, or intuition, we determine the probability of something happening. An executive might decide that a new product has a 70% chance of success. That's his opinion. Someone else might believe that it only has a 20% chance of succeeding. The basic requirements for assigning probabilities are that the probability of an experimental outcome I, denoted by P parentheses E subscript I, is between 0 and 1 for all E subscript I's. And when we add up all the probabilities for all the possible outcomes, it must equal 1. So let's say the probability of rolling a 1 on a die is 1 out of 6. Then the first basic requirement is satisfied. The probability is 1/6, which is somewhere between 0 and 1. Let's see if it satisfies the second requirement, that is that the probabilities of all the possible outcomes have to add up to 1. The probability of rolling a 1 is 1/6, and the probability of rolling a 2 is 1/6, and the probability of rolling a 3 is 1/6, and the probability of rolling a 4, 5, or 6 is also 1/6. So when we add up 1/6 plus 1/6 plus 1/6 6 times, we get 6/6, which is equal to 1. Now we all seem to know that the probability of a head is 50-50, and we all seem to understand the probability of rolling a 3 or a 1 or whatever on a die is 1 out of 6. But this is the formula for calculating the probability of something occurring. The probability of an occurrence is x over t, where x is the number of ways an event occurs, and t is the total number of possible outcomes. So back to our example of picking an ace out of a deck of cards. X is 4, there are 4 possible aces, 2 reds and 2 blacks, and t is 52. There are 52 possible cards, or outcomes. So the probability of an ace is 4 out of 52. Let's review some of the terminology and concepts that are used in probability. First, let's define the term event. An event is defined as each possible outcome of a variable. A simple event is described by a single characteristic. So for example, rolling a die can result in 6 possible outcomes, and these are simple events. A joint event is an event that has 2 or more characteristics. An example of a joint event would be tossing 2 coins and getting 2 heads, or picking a red ace, and so you have a card that is both red and an ace. That would be a joint event. And finally, we have something called the complement of an event. The complement of an event, say event A, includes all events that are not a part of A. The symbol for the complement of A is A prime, the letter A with a prime symbol that sort of looks like an apostrophe. So if event A is defined as a red card, then all cards that are not red would be A prime, or all black cards, assuming this is a standard deck of cards with red and black cards. Let's talk a little more about the complement of an event. Here's a diagram called a Venn diagram, which helps us to visualize this concept. Let's say that the blue circle is event A, then everything else around the circle contained in the red rectangle would be A prime, or the complement of A. And finally, the sample space S is defined as everything contained in the rectangle, both A and A prime. Since the sample space contains all the possible outcomes, both A and A prime, then the probability of A plus the probability of A prime must equal 100% or 1. And from this we can compute the probability of A using its complement. If the probability of A plus the probability of A prime is equal to 1, then the probability of A is 1 minus the probability of A prime, since they both have to add up to 1. The addition rule is useful when we are interested in calculating the probability that at least one of 2 events will occur. When we want to know the probability that event A or event B or both may occur, this is called the union of 2 events. The way we write union is with something that looks like a U, so it's read the probability of A union B. This Venn diagram helps us to visualize the union of 2 events. The 2 blue circles represent the union of both A and B. The overlapping portion of the 2 samples in the middle is called the intersection of A and B. The intersection of 2 events is denoted by an upside down U. So while the union represents A or B or both, the intersection is A and B. So for union we say A or B, and for intersection we say A and B. The overlapping piece in the middle of the 2 circles here is the intersection of A and B. So that brings us to something called the addition law, which gives us a way to compute the probability that event A or event B or both will occur. In other words, it helps us to compute the probability of the union of two events. The formula for the addition rule is shown in the red box. The probability of A union B is equal to the probability of A plus the probability of B minus the intersection of A and B. We can visualize this formula as follows. The union of A and B is equal to event A or circle A, shown by this circle, plus circle B, minus the intersection or the overlapping piece of the two circles. Why do we subtract out the intersection? Why don't we just add A plus B? Well, if you think about it, when we add circle A and circle B, we are double counting the overlapping piece. We are counting it twice, once as a part of circle A and once as a part of circle B. So we have to subtract it out one time, and that is why the formula is A plus B minus the intersection. Let's take a look at an example using a contingency table. Here we have a sample of 50 people who were asked if they ordered a vegetarian meal or not. It was also noted whether they were male or female. The results are shown in this contingency table. So let's say we want to determine the probability of ordering a vegetarian meal or the customer being a male. So that would be vegetarian or male or both. Let's use the notation of V for vegetarian and M for male. So using the addition rule, the probability of V union M is equal to the probability of V plus the probability of M minus the intersection of V and M. So what is the probability of vegetarian and male? Well, look at the contingency table and we see that 16 people ordered vegetarian out of a total of 50 people. So the probability of V or vegetarian is 16 over 50. And how many people were male? Well, that would be 26. So 26 out of 50 would be the probability of a male. Then we have to subtract out the intersection. So what is the intersection of V and M? There were 6 out of 50 people who were both male and ordered vegetarian. So the intersection would be 6 out of 50. Now we're ready to put these numbers into the formula to calculate the union of V and M. And that would be as follows. 16 over 50 plus 26 over 50 minus the intersection of the two, 6 out of 50, and that gives us 36 out of 50. So that's how we calculate the union of vegetarian and male. Remember, union means or, so that would be someone who ordered vegetarian or is a male or both. The addition rule we just used to calculate a joint probability, the probability of A plus the probability of B minus the intersection of A and B, has one variation to the formula, the case where the two events, A and B, are mutually exclusive. Two events are mutually exclusive when they have no sample points in common. So if event A occurs, then we cannot also have event B at the same time. Being 30 years old or under is mutually exclusive from being over 30 years. You are either 30 or under, or you're over 30. You can't be both ages at the same time, so those events are mutually exclusive. So the addition rule for mutually exclusive events is the probability of A union B is equal to the probability of A plus the probability of B. So we just add up the two probabilities, we don't subtract out the intersection. Why don't we subtract out the intersection? Because there is no intersection. With mutually exclusive events, there are no sample points in column, so A and B will never overlap. Here is a Venn diagram showing events A and events B when they are mutually exclusive. By definition, if an event is a part of A, it cannot be a part of B at the same time if they are mutually exclusive. So as you can see by looking at the Venn diagram, there is no overlap, so the formula for calculating the union of two events is simply the probability of A plus the probability of B. We have no intersection to subtract out. Oftentimes, the probability of an event is influenced by whether a related event already occurred. If we are given information about a related event that already occurred, then a new probability using that information can be calculated. That new probability is called a conditional probability. Let's take a look at a cross-tabulation showing males and females and their dinner orders. Again, we have 50 customers, 26 males and 24 females, and we have 16 customers who ordered vegetarian meals and 34 customers that ordered something else. This table shows the distribution of males and females and their orders. Now let's say, for example, we know that a customer is male. Does that change the probability that the customer ordered a vegetarian dish? If it does, then being male is related to the entree that the customer orders. The notation for conditional probability is written as follows. P, then in parentheses A with a vertical line, and then B. The way this is read is the probability of A given B. The vertical line is read as the word given. So it is the probability of A given B. So if we let V stand for vegetarian, and V prime stand for other orders, and M is for male, and F is for female, then the conditional probability of a vegetarian order, given we know the customer is a male, would be written as P parentheses, V vertical line, M end parentheses, but it is read as the probability of V given M. The given information is always written after the vertical line, so it is always the probability of event A given event B. Here we are told the customer is male, so that's the given information, M for male, so we write the conditional probability V given M male. Before we calculate a conditional probability, let's review the calculations for something we have already learned, the intersection of two events. Remember, the intersection of two events, when two events happen together, is the overlapping area in the Venn diagram. How would we calculate the intersection of male and vegetarian? Well, if you look at the cross-tabulation of orders by gender, you will see that the intersection of vegetarian orders and males is 6 out of a total of 50. So the probability of male intersection vegetarian is 6 divided by 50, which is 0.12. How would we calculate the intersection of male and not vegetarian? That would be the probability of M and V prime, and looking at the table we can see that is 20 divided by 50, which is 0.4. These probabilities are called joint probabilities since they give us the intersection of two events. We can also look at the margins of the table to get the probability of each of the events separately. Remember, we call those simple events. For example, we can take the probability of a customer being a male. We can do that by looking at the margin and seeing that there are 26 out of 50 customers who are male. So 26 divided by 50 would give us 0.52. And the probability of a vegetarian order is 16 divided by 50, and that would be 0.32. We get these probabilities by looking at the margins of the table, so these are called marginal probabilities. We can also get the marginal probabilities by summing the joint probabilities. So for example, the marginal probability of a male is the joint probability of males ordering vegetarian and male not ordering vegetarian. So the probability of a male is 6 divided by 50, the intersection of male and vegetarian, plus 20 divided by 50, the intersection of male and non-vegetarian. So these two joint probabilities, the intersections of the two events, add up to the simple probability of a male. 0.12 plus 0.4 is equal to 0.52. And we saw before that 26 divided by 50 is 0.52. Now we are ready to learn how to calculate conditional probabilities. Remember, we wanted to know what the probability of a customer ordering a vegetarian dish is if we know the customer is male. We can calculate this easily if we have a cross-tabulation table. We isolate the column with just the males, so there are 26 males, and then we look at how many of those males ordered vegetarian, and that's 6. So we can simply divide 6 by 26, and we get the probability of a vegetarian given that they are male. So we see that the conditional probability of V given M is the joint probability of M intersection V divided by the probability of M male. The formula for this is given as follows. You can see the numerator is the intersection of A and B, and the denominator is the marginal probability of B. So the formula is written as the probability of A given B is equal to the probability of A intersection B over the probability of B. The formula is always divided by the given event. So in this case, if B is given, that would be in the denominator. We can also write the formula to find the probability of B given A instead of A given B. It all depends on what given information we have. Let's put some numbers in this formula and calculate first the same probability we did before using the table and our reasoning skills, and now let's do it using the formula. So using the formula to calculate the probability of ordering vegetarian given that the customer is male, we write P, parentheses V, vertical line M, and that is read as the probability of a vegetarian given a male. And that is equal to the probability of vegetarian intersection male divided by M, male. And that is 0.12 over 0.52, which is 0.23. Now, what if we wanted to calculate the probability of a vegetarian given that the customer is a female? Well, that would be written as the probability of a vegetarian given a female is equal to the probability of a vegetarian intersection female divided by the probability of a female. So that would be 10 out of 50 for the numerator, the intersection of vegetarian and female, divided by 24 out of 50 for the denominator, the number of females out of the total, which is 0.2 over 0.48, which is 0.4167. You can see that if we know the customer is male, the probability of ordering vegetarian is 0.23. But if we know the customer is female, the probability of a vegetarian order nearly doubles to 0.4167. So knowing that the customer is male or female changes the effect or changes the probability of what they order. Or to put it another way, females in this case are more likely to order vegetarian entrees than males. That makes the two events, dish ordered and gendered, dependent events. What if knowing the probability of event B has no effect at all on the outcome of A? When knowing some information about event B has no effect on the probability of A, then the two events are considered independent events. Written formally, two events A and B are independent if the probability of A given B is equal to or the same as the probability of just A. So for example, what is the probability of picking an ace from a deck of cards given that the card is black? Well, there are 26 black cards and 2 black aces. So if we know a card is black, then there are 2 out of 26 chances of the card being an ace. Well, let's say we don't know if the card is black. Then what is the probability of an ace? Well, the probability of an ace is 4 out of 52. Since there are 4 aces out of a full deck of 52 cards, both colors, so the probability is 4 out of 52, which is 2 out of 26. So the probability of an ace given that it is black is the same as just the probability of an ace. Therefore, the two events are independent events. We can use the multiplication rule to compute the probability of the intersection of two events based on what we just learned about conditional probability. Here is the formula for the multiplication rule. If you look back at your notes on the formula for conditional probabilities, you will see that this formula is derived from that one. Just here we're solving for the intersection of two events, and we use the conditional probabilities to solve for it. And in the other case, we were solving for the conditional probability and we used the intersection to solve for it. Algebraically, the two formulas are the same. So let's see how we would use this formula. What is the probability that a customer is both male and orders vegetarian? Okay, so the probability of a male is 26 out of 50. And the probability of vegetarian given male is 0.12 divided by 0.52, which is 0.23. And we got that before, if you look back in your notes. So then the probability of a vegetarian intersection male would be the probability of male, 0.52, times the probability of vegetarian given male, and that would be 0.23. So 0.52 times 0.23 is 0.1196. And that is how we will calculate the intersection of two events using the multiplication rule. What about the case where the events are independent? When the events are independent, the multiplication rule is simply the probability of A intersection B is equal to the probability of A times the probability of B, since the given information doesn't affect the probabilities. So since we already determined that an ace and a color card are independent events, let's use that as an example. What is the probability of the intersection of ace and black card? We can easily figure this out intuitively since there are 2 black aces in a deck of 52 cards. The probability of picking a black ace is 2 out of 52. Using a calculator, we get 0.03846. We can use the formula, and the probability of an ace intersection B is equal to the probability of black times the probability of ace. Remember, they're independent events. So we take the probability of black, 26 out of 52, times the probability of ace, 4 out of 52, and if we multiply using a calculator, we get the same 0.03846. When a problem is complicated and intuition doesn't work, it's always a good idea to have the formula to fall back on, but you should understand the logic of why it works. So when events are related, we say they are dependent events and use the conditional probability formulas for dependent events. If the 2 events are not related, then they are considered independent and the probability of either event is not affected by the other event. This tutorial contained a lot of information and I hope you were able to take it all in. The next 3 slides show the important formulas you will need for solving problems in probability. Pause this video and write these down. You will need them. Here's the first slide. Remember I said there are 3. Here is the first slide with the formulas for combinations, permutations, and the complement of an event. Okay, pause this and write this down. Here is the second slide reviewing the formulas for the addition rule for calculating the union of 2 events and conditional probability. And here is the last review slide for the multiplication rule for calculating the intersection of 2 events. As I said, you will need these formulas if you're going to do any serious calculations in probability or if you will be doing some advanced studies using probability. Pause the video, rewind, and write these down. I hope you enjoyed this tutorial on basic probability, and I hope you learned something.